I work here at CIBSE in a small department, the membership services team, which looks after a lot of our regions, groups and societies. We host events through providers. That's all I wanted to say, really. I just wanted to introduce our speaker, Andrew McKenna from Global Associates. He's the Operations Director. Some of you may have been present for the last session for the part 1 in October. If you weren't, we will post the link to that session so you can go back and watch that, then followed by this one. So I think that'll be useful for everyone. But yeah, without further ado, I'll hand over to Andrew.
Thanks, Julian. So yes, thank you. So as Julian said, I'm Andrew McKenna. I'm the Ops Director for Global Associates, wonderful company. Predominantly, we are a BMS projects and service delivery company, but we have a big ethics on energy efficiency, actually, and it's a big part of what the second installment of the introduction to BMS Part 2 is. I'm probably just going to start, actually, with a quick recap just on the first introduction to BMS. It's essentially just a quick snapshot of the kind of topics that we covered, but as Julian said, there is a link hopefully available to if you missed that and you want to get back into it. But we talked about a number of things: the who, the what, the why, the where, the when, all pertaining to do with the BMS system. So we talked a little bit about the need for legacy systems and how to identify the types of legacy systems. We talked a bit about networks and how the construction of networks and third-party equipment can kind of come together. We talked about the constructs of a panel. A lot of the times we identified that there's a lot of people out there who kind of see a panel and the first thing they understand is not really knowing how to navigate the different elements within a panel. So we covered that. We then talked about the types of equipment, both from an industrial and commercial setting you should expect to see linked to a BMS system. We talked about the evolution of systems from a networking perspective, going from the the early years of the 90s right the way through to today. We covered some of the problems you're likely to come across through bad planning within a BMS system. And as I said before, we also talked about kind of obsolescence and posed the question of when is obsolete. So that's kind of the first edition. There was a lot more to cover, but I just wanted to give a snapshot of what the first introduction was. This installment is probably a little bit more technical. I've got to be honest. There's probably a few more concepts in here that do speak to the more technical nature of the BMS side, but actually quite poignant for energy efficiency. So what we're going to kind of speak about, the theme of today is really the heart and focus is all about energy and then soft landings and what that actually means. And we're going to do that almost through a story, so a navigational journey of all the real world problems that energy managers and facility managers and building owners kind of face today. Somewhere along the line, they're at a step or a stage within a building and maybe don't quite know what the next level looks like to get to your targets. We're going to show you how we do some data analysis, ultimately how we create a baseline plan, then provide those energy conservation measures from that analysis, display the results, show the importance of continued monitoring, and then the 5 key steps of soft landings and kind of what that means. We'll discuss that in a more broad a bit later on. So first thing that I always think, and it wouldn't surprise me if everyone's come across this term, is what you can't monitor, you can't manage. So data is usually the first step. It's key to understanding how your building's operating. So as I said, we're going to tell this through a journey. So let's assume we've got a factory, and within this factory we've been notified by a client, picked up the phone, and he's got a problem. The energy bills seem high, and for them there's no way to identify if those bills are actually normal or abnormal. We tend to see that a lot. A bit of information we found out is actually that there's only one main electricity meter and there's only one main gas meter. Some other information that was available was the electricity over a 5-year period roughly averages about 1.1 megawatt hours of energy in relation to electricity, and about 1.7 megawatt hours in gas. That's over a 5-year period. It's without any energy price inflation. It's more of around to be able to kind of navigate a journey. So if we look at that in pounds, shilling and pence as a cost, you know, on average, this factory is paying 150 grand a year in electricity, and it's paying 60 grand in gas. What else do we know about this factory? Well, the factory is split into process machinery, HVAC equipment, lighting, and power. But the clients also informs of some other additional detail, which is going to become apparent as quite important. So firstly, the size of the site is 15,000 square meters. And that the factory is roughly split 50-50 by area of process control and office space. So 50% of it is process control, 50% is based on office space. But we also know that there's an on-site cafe and a dining area. So from an information perspective, we know that there's only 1 meter on site for each of the utilities. We know that it's 15,000 square meters, and we know how much energy they're spending on an average year. So that information alone is not enough, though, is it? Because if you think about it, from our perspective, even without trying to draw a line in the sand, the first thing you have to conceive is that, well, if we know there's process machinery, we know there's HVAC equipment, we know there's lighting, and we know there's power, and we know they're paying 150k average per annum, we have to make an assumption that it's an equally equated energy usage, because there's only 1 meter. It's a big problem. And we have to, also concede the fact that there's heating and there's a kitchen. Therefore, we have to assume at this stage, even though it's probably wrong, that it's a 50-50 split on gas. So this is all to do with just a lack of knowledge at this stage. We know that they're using energy, and we know what kind of equipment's on site, but we don't know enough detail at this stage. So this is the most important step. A lot of people, what tends to happen is, we all get our solution heads on and we jump straight into site and we start thinking of all of the great energy conservation measures, which are probably great and right, but actually there's no real line in the sand to understand, what that even looks like. So the most important thing for most people at this stage is, look, you're using energy, you don't know whether that's good or bad. Let's benchmark the site. And there's a lot of different types of benchmarks. The CIBSE's benchmark, there is Carbon Trust's benchmark. There's a lot of different ways. It's a simple calculator, and there is a number of factors that can sway the information, but ultimately you need somewhere to start. So, just by plugging in some basic information, we know it's a manufacturing plant. They provide general manufacturing. We know it's 15,000 square meters. We know they're paying 150k per annum on electricity, and we know they're paying 60k per annum on gas. And with most benchmarking tools, they try and look at what the profile would potentially look like or for that type of building. And whilst it's always nice to have, it probably doesn't paint the right kind of picture, but it's a good indicator of where they assess the energy is being used from a percentage perspective. Okay, so first and foremost, the benchmark has said to us, look, your site is 13% over best practice. So you're using 13% more energy than what best practice looks like. And therefore it's performed below the industry standards. And by that convention, actually, with implementing some of the energy efficiency measures, you could save £24,000 per year based on that basic information. So now we have some information to start with. We can think, okay, well, we're performing worse than what the best practice looks like. So what's next? Well, now we have to think about a baseline plan. So we as experts, I guess, within the field and the industry, have to think about what that means on site, how we can kind of help and guide. So we have a 4-step plan. First and foremost, we have to submeter. We have to get more granular than what's currently on site. That's the first principle. We have to understand, as I said before, what you can't monitor, you simply can't manage. Step 2, we need to analyze that data. We need to understand, where the data is being used once we've got to that granular level. Then, and only then, do we provide the energy conservation measures against what that analysis is telling us. And then finally, and more importantly, we need to continuously monitor that nice optimized site once we've done that. So that's the 4-phase plan that we do from a baseline. So let's start with the submetering strategy. So first and foremost, this is the current setup on site. We have a main meter. We know it's split and distributed between, 4 outlets. We have process control, HVAC, lighting and power. So what options do we have? Well, option 1, we could submeter each distribution and link it all via a common protocol. In this case, it would be Modbus through to a gateway. That gateway would then go to the main BMS system. That would allow us to, at least understand from a class of distribution what it's being used at each element. So that would be a really good start, good option. Option 2, so finances was more of an issue, and maybe the sub-circuits was too mixed distributed, i.e., you've got power and lighting and process all kind of mixed together, and it's really challenging to split the networks. Then maybe another option would be a non-intrusive load monitoring. You may have heard the term NILM, N-I-L-M. What is NILM? Well, NILM is a way to disaggregate your main incomer. NILM works by essentially realizing the harmonic frequencies of different asset classes. So as an example, the signature of a light will be a completely different harmonic frequency or signature of a motor or a compressor, as an example. So what the non-intrusive load monitoring is capable of doing is read all the harmonic frequencies that's coming through your main incomer and then split that out or disaggregate that into classes of energy use. So that's a really good way, which is a lot more reduced cost than perhaps a costly submetering solution, to still get some level of disaggregation, which is ultimately what we're trying to get to. But as I said before, what you can't monitor, you cannot manage. So we're going to go with option 1. We sat down with the client, we've discussed the options, and the client wants to go with a submetering strategy. Okay, great. So now we're going to analyze that data. So before we even started, we looked, this is the general profile. What can we learn from this profile? Well, straight away, the base loads, or the bottom of this top hat, it looks like a top hat. You may have come across that top hat reference. The bottom of the top hat, it's it's actually over half the usage of the total profile. You're using like at maximum maybe 90 kilowatt hours per half hour. Per half hour. Whereas the bottom of the top hat's about 50. So on average, that's a really high baseline. So that's the first thing that sticks out that we need to review. Although it looks quite uniform at the top, it's still a little bit kind of stipply, and there's probably things that we can do. The startup performance, you probably assume, somewhere around 4 o'clock, things seem to ramp up, and then they really ramp up around 7 o'clock. So there's things that we need to analyze. So by putting in the submetering strategy, which we've gone from an initial analysis of an equally equated energy use across the 4 streams, we now know where that energy is being used at a much more granular level. So we understand that the process machinery is using 30%. We know the HVAC equipment is using 35%. We know that the lighting is using 20%, and we know that the power, so things like PCs and IT equipment, is using 15%. So at this stage, whether that's right or wrong or best practice, we don't know. But what we do know is that that's the subset of what energy is being used at this this factory. So let's run the numbers. So what have we got? Based on these numbers, and based on the fact that we're using for electricity as a guide, we're using 150k per annum on average. So the split of energy, because what we're trying to get to here now is to figure out, okay, so as a provider of efficiency measures, where can I affect change? There's some areas that I can't affect change. As an example, the process control. It's the lifeblood of the factory. They need to use these process machines. Maybe there's more efficient use of the machines, but that may be a big, a large investment. So we're trying to get to the point now of saying, well, what can we affect? But by submetering the whole factory and at least understanding where we can use the differences, we know what costs we've got to play with. So 45k of that of that energy is being used for process control. 52.5 is being used against HVAC. 30k is being used for lighting, and then 22.5k is being used for the power for things like IT equipment and PCs and whatnot. Okay. When we split out that data into the own individual profiles, there's a few things that strike out. I mean, the lighting, it looks to me like it never goes off. You know, it's uniform, it's constant, it's almost like it's 24/7. The same can be said for power. Yeah, we look at the process equipment, and again, the base load is still quite high, and then it kicks in around 5 a.m. And then the HVAC again, there's things happening overnight, which is really equating to a really large rise in energy, and probably, you know, from an efficiency perspective, is grossly underperforming. So obviously, by being able to split these things out, the analysis element really comes in, so you can get down to a more granular effect. We know we have to start thinking now logically about what we can do and what we can affect. So as a BMS company and as someone who thinks about energy, you know, when we're detailing sites, the first thing, you know, we go for is, because, you know, you look at the low-hanging fruit and you look at the kind of small to medium investment is normally the best way to get, you know, the biggest bang for your buck initially as a first starting point. So we'll always guide towards the HVAC and the lighting, because they're the ones, you know, we can definitely affect change in and quite rapidly. So based on that value, you know, for building a business case, we know how much energy is being used specifically in them two sections. So what now? Well, as I said about the BMS system, for me and for us, for our team and for our industry, we'd probably assume and assess that the BMS system is the most powerful tool to manage energy. You know, there's things out there, there's energy suites, but actually it's the things that get at the heart of how your plant is running on site is the biggest way to manage and monitor energy. In reality, it has the power to control over 80% of the site's use, which is quite profound. Actually, a study was done by the Department of Energy and Climate Change, which looked at you know, a whole suite of building types to try and understand what kind of energy is being used, and also what's on the where it's being used ultimately, and can it be on the BMS. And in reality, you look, so heating and ventilating and cooling 52%, 19% of that is attributed to lighting. You know, you have hot water 9%, with the next 20% being catering other and computing. So in reality, that's quite an amount of energy that can be under the dictates of a BMS system. So the message here is to try and get as much data and information from your systems onto the BMS system, and we'll go on to why that's important shortly. Okay, so let's just take a quick break. So what have we done? We've had issues from the site. We know that they're using energy. They don't know where they're using energy. We've assessed that actually that they've only got 1 meter, and we don't really know enough about the site at this stage. We sat down with the client. We put a submeter strategy in. So now we've got to an analysis phase where we've understood where that energy is being used. So now we want to get more in depth in the site. We want to know intrusively, how is that site using energy? You know, what plant and equipment, what assets are being used on site? So really understanding the site in its entirety. So what do we do? So we start with a survey. So we look at the site assets. So we've gone to the factory. We've identified that there's fluorescent tubing throughout. There's an obsolete closed protocol BMS system. There's 3 60 kilowatt boilers. There's 125 kilowatt chiller. There's an 80 kilowatt domestic hot water heater, which is standalone, gas fed, so it's not on the primary circuit. There's a main primary ventilation air handling unit. It's got a 15 kilowatt supply fan, which is star delta. It has an 11 kilowatt extract fan, which is also star delta. It has a preheat coil, a chill water coil, and a reheat coil. And then you've got these standalone gas-fired heaters that are controlled from a fixed thermostat for the process area. So dotted about the process area, which is 50% of the site, you've got these units, distributors that are providing just standalone heat from their own control wall stat. We also have some various AC units in the offices, and we have fan coil units throughout the office areas that in total equate to 75 units. So now it's really time to solution. Now it's the time when we've identified how the site's operating and what it is, how to solution such. So now we come to the energy conservation measures. So we've sat down, we've understood what the site's doing, and we start to map things out. So what are we going to do? We're going to put a new LED lighting solution throughout to replace the twin TA fluorescent tubes. That lighting needs to provide daylight harvesting. Daylight harvesting is really a way in which you utilize natural light, which is being monitored by sensors within the light fittings that decide on whether a specific output needs to be driven. So as an example, if you require X amount of lumens to light a specific area, if the daylight is providing enough of that, then the lights closest to the light will dim significantly. So that's what daylight. So daylight harvesting is a way to reduce your light output where natural lighting can replace that. In the hallways where there's no permanent use, we have follow me lighting, and we also have zoned motion detection. We need this lighting to communicate over BACnet, which is a common BMS standard. And we also want the lighting to incorporate Bluetooth 5.0, Zigbee, LoRaWAN, or N-Ocean, or any combination of them. These are all wireless communication standards, and there's a real important point as to why I think that's really, really significant. So think about, we've already agreed that they've got a really old lighting system, and we're going to replace the lighting system with a new one. So we're going to get the energy efficiency benefits from that. But actually, we're also going to get the benefits from the technology that we're installing because of today's modern technology. That's going to allow us to utilize the wireless framework in a way that presents data back to the BMS system, therefore reducing additional costs. So what's the business case for this? After we priced everything up, working with partners, we come to 73K. So we know we've got a starting point in relation to a business case. What else are we going to do? Well, we know we've got an old legacy BMS system, so we want a brand new open protocol BMS system. We need that BMS system to have full control over all the HVAC assets, and we're going to employ enhanced energy-based software, enhanced over your standards. You can pick a standard, enhanced over that. And we're going to replace all of the field devices with new field equipment, sensors, actuators, differential pressure switches. And we're going to integrate the motion sensors from the lighting to be utilized as a data available for the BMS for occupancy monitoring. Very important to reutilize data that's already available to us without having to double up on equipment. And again, with this lighting system, we'll communicate via BACnet. And we're also going to provide a new head end that shows the full scale of the functionality with IP-based software, with energy targeted functionality. The business case on this one for the full turnkey installation is 60K. What else? We're going to replace the Star Delta motors with variable speed drives, and we're going to integrate them into the BMS with a variable speed output as an analog output from the BMS. Business case for the installation, 3K. And then what we're going to do is we're going to utilize the wireless communication available to us through the lighting system, and we're going to install indoor air quality sensors that are going to map the process area. We're going to install wireless relay modules that are going to control the existing thermostats of each of the gas-fired units on the process control area, because that's going to provide us some real close control. Currently we've looked at the baselines, and what we do know is that things tend to be on 24/7 or running overnight. So by putting proper control in, the data coming back to the front end, we're going to be able to capture that data and control it, which is the most important. I'm going to integrate that information over Zigbee through the lighting circuit, and then that will be converted to BACnet into the BMS. And the wireless installation business case, 12K. So I talked about this energy enhanced strategy. What do I mean by that? Well, this is probably where it gets a little bit technical, and there'll be people who'll be able to follow, maybe people who might not be able to follow. But what I would say is, any questions, anything we want to come back to is absolutely fine at the end. But this is how we would approach it. So look, all time clocks are going to be set to realistic values to suit the building's operational needs and functions. why, it's an obvious one, but it's critical. Schedules are normally the first place an engineer or, someone will go to and just extend the time. And depending on the type of system you have, you may not have the ability to employ a fallback strategy where the time zone or the schedule for a specific item of plant reschedules. And the problem with that is, left unabated, it's almost like putting things into hand. It's not great. So by employing a really good strategy to identify change is key. And this can be done by making sure the access rights for the schedules are only allowed for users who are deemed worthy. The calendars in most systems now can be set up with company standards. They can allow a revert back status as well for, an agreed profile of what that schedule needs to do. What else? Look ahead weather optimization. Why would we want to do that? Well, convention is we optimize based on, the internal and external temperatures, and we try and calculate through software. But actually, modern systems nowadays, we have the ability to actually get the forecasted data from the weather station. And the reason that's so important is because you can get your building prepared much earlier than what your traditional software does, but with real data. And that's a big advantage for not wasting heat or wasting cooling. So using look ahead technology is absolutely crucial for an energy efficient system. What about PID loops? Look, PID loops or having control or proper tuning of PID loops is critical. If you think about a PID loop, think about you're driving along on the motorway and you're trying to maintain a speed of 70 miles per hour, and you've got your foot on the accelerator, and you're eyeballing it, so that's your feedback. And the moment you go up a hill, you have to press the accelerator down to increase your speed or increase the amount of engine the work has to do to maintain 70. But the problem is it's not accurate, because if you're trying to do it by your foot, you may overshoot and go over the speed, or you may undershoot and then you drop speed. But if you put your car into cruise control, almost certainly it's going to maintain 70 miles per hour, whatever's thrown at it, whether that's an incline or a decline, because it has the ability to map what it needs to do from the engine's perspective, whether it needs to accelerate or decelerate in order to maintain 70 miles per hour. And in reality, that's exactly what a PID loop is. It's a way in which it tries to calculate the influences that change the dynamics. So as an example, you think about a valve when you're trying to maintain a static set point, things change. The demand on the system can reduce more of the return water that comes by. So you have what's called a set point, and then you have your process variable or the temperature, or also known as the feedback, which is either over or underneath the set point, and that's effectively called the error. So that's the amount of difference between where your set point is and where it needs to be, or the temperature needs to be. So what the loop does is a series of calculations that really try to identify what it needs to do to reduce that error. So we have something called proportional and another thing called integral. So the proportional element is really just to say, well, for every degree I'm out, add X amount to the output in order to try and get there. The problem with that is the moment you reach your set point, your output is at zero, and that's not great because you're never really going to hit your set point. So what the PID loop does really is to introduce something called integral. And the best way to think about integral really is to think about how long the time needs to be for the system to be open 100% in order to not overshoot the set point. So as an example, if I'm saying I need the valve or the supply water to be 70 degrees, how long does this valve need to be open at 100% for that output to be satisfied or the set point to be satisfied? And it's a mind thing. So depending on what you're dealing with, it's a different way to think about it. As an example, the space environments, if you're supplying, temperature into a space, the chances of you saying, well, it's 19 degrees, now I need it to be 21 degrees, it's, there's that 2 or 3 degrees in a space can take quite a long time. So your integral action needs to change there based on that longer time. Whereas, for example, if you're controlling the speed of a fan, you know, the moment you add another couple of percentage onto a fan, it's almost instant. So how long does that change take to effect? Well, it's instant. So them calculations are absolutely key to remove what's called hunting or overshooting. It's quite a complex thing to describe when you're trying to describe it in words, but actually the simplistic way to think about it is, you know, exactly how I tried to explain with the car. You're trying to go, you know, a certain speed, and you're using the output of your foot to generate the speed in order to maintain a specific value. So clearly, you know, not having a good tune loop is quite critical. Well, for a number of reasons. Number one, you're trying to reduce or mitigate the hunting, which is the overshooting and undershooting. And obviously, a poorly controlled loop is really negative for impacts of big variable swings and erratic temperatures, or you know, supply air or whatever you're controlling your loop from. Okay, so the next one is back with time. So during optimized startup and prior to occupancy, only floor level units, so fan cool units and boilers are on, with supply air remaining at its minimum speed. So that's important in relation to a number of things. Well, first and foremost, we want to reduce the amount of energy being used on start and startup and cool down, because AHUs and big users of energy, you know, if we can reduce that, that's first and foremost, you know, the most key thing. But actually, you know, if you run your fan at startup with everything else, you're normally introducing a lot of fresh air, and that's counterproductive from an energy perspective. So why do we do that? Well, obviously the main issue provides fresh air, and it becomes counterproductive to run that. So instead, reduce your fan. We're going to reduce the fan to its minimum speed, and we're going to only run the boilers and or the chillers with the fan cool units until we hit standard occupancy, and then we slowly introduce the fans. Another one. So this relates to how we control boiler flow and also the pumps. And typically, what you tend to see in a lot of specifications is we tend to say, well, you know what, we're gonna control the pump speed purely based upon the position of the valves as a demand. So if the valves are at 100%, as in requiring heat, therefore we will run the pump at 100%, because, you know, providing all your loops are being tuned, that's the right thing to do. But actually, I and others like me would counter that, because for me the most important thing is trying to reduce the work done by the boilers and the chillers if they're not required. So how do we do that? Well, you think about your circuits on site. You typically have VT circuits that are for your radiators. You may have CT circuits, which are providing your coils for your ventilation units and your fan coil units and your main air handling plant. And then you have things like domestic hot water. But in our scenario, we've got a standalone gas unit. So really, all we've got is a circuit for the fan coil units and a circuit for the main AHU. So do we really want to run our boilers at 100% all of the time? You know, think about the delta T across your main battery. Let's be honest. When you start getting into the shoulder seasons, you know, 80 degrees is probably too hot. You know, we're probably getting 15 degrees coming onto your main ventilation coil, and quickly getting to your 21 degrees or 18 degrees or 19, whatever your set point tends to be for your main AHU, quite quickly. And therefore, you know, your boiler really is just maintaining this 80 degrees, and the system's getting rapidly up to temperature quite quickly. So let's use the supply air temperature set point and the temperature itself as a way to start cascading the control for both two things. Number one, the pumps. So let's first use the pumps to speed up when there's a demand. If that demand can't be reached, then we start to creep up the boiler set point. So what I'm trying to say by this is, by reducing your boiler set point, instead of having your standard 80 degrees, there's a minimum threshold that we can run the boiler at. And then we start incrementally bringing that up based on the demand of the CT circuit. And that's purely going to be based on whatever that maximum is. So, you know, let's talk about the VT as an example. The VT circuit typically runs at 80 degrees when it's 0 outside and somewhere around 20 or 30, based on when it's in 20 or 20 degrees outside. So whether these two circuits both have a maximum requirement for demand, so using either or of them should be the first point in which you use to calculate your boiler flow. I did say this was going to be a complex conversation. I hope you're still with me. What I'm trying to say here is I believe this is a better way. We believe this is a better way to control, from an energy perspective, both your pump speeds rather than using valve positions, but actually use supply air set points as a way to understand what your maximum demand is. Next. Okay, so heat and pumps serving office and fan coil units. So again, this is just standard kind of summer base set point, but actually heat and pumps that specifically serve the fan coil units are going to be off when the temperature outside is above 15 degrees. Why? Well, there's a trade-off, obviously. If you think about it, inside you've got process machinery, we have people moving about, we have PCs, all generating enough heat. So what we're saying is if outside's at 15, it's a fair reflection to suggest with enough heat and body heat being generated, that somewhere between 19 and 21 degrees is enough to not require the CT circuit that's providing the fan coil units or the specifically those pumps. It's a really good way of reducing energy. No different from the cooling. So again, the cooling pumps or the chill water pumps to the FCUs will be off if it's less than 10 degrees outside. Why? For the same reason. We can use free cooling strategy. So using the fresh air from outside to mix with the return air from the plenum in order to give you free cooling rather than using the chiller. All supply air temperature set points are to be rescheduled between limits from space, return, or outside as appropriate. Why? Really, we just want to reduce the demand on the plant. So we want to utilize the data that's in and around, whether that's outside or whether it's in the building, in order to be able to say, well, rather than providing a static set point in your supply air at, 18 degrees or 19 degrees, actually let's use the feedback from the environment in order to give a more precise supply air set point. That's number one, going to aid in the requirement for the main fan coil units, whether it needs more heat or whether it needs more cooling. So you can range that somewhere between a minimum threshold and a maximum threshold in order to get you that right level of data and right level of demand. Because you got to think, if you're providing a static set point to a plenum, maybe 20 degrees, and there's a real cooling demand on site, well, the first thing you're going to do is all your fan coil units are rapidly going to ramp up. But actually, if you're plenum, if you're starting to produce some more cooler set point in your plenum, it's less work for the fan coil units to have to do. That's essentially the concept. Sticking with set points, all proportional set points to utilize reset strategy or limited strategy. So why is that? So again, proportional set points, they're just usually a characteristic of some other value that's acting upon the system to create an automation of a set point. So think of like a variable temperature on the radiators. The radiator temperature, the reason it's variable is simply because it changes purely depends upon the temperature outside. So it's a completely proportional scale. So if outside is really cold, your radiators will be really warm. If as outside gets warmer, your radiator temperature will be cooler. It's just the way kind of the scale operates. But the big problem with that is a lot of the times that kind of strategy employed doesn't take into effect things like fabrication within the building, so how well insulated the building is. So when you are providing really hot, 80-degree temperature because 0 degrees outside, quite quickly the space could get really, really warm. But actually the problem is it's too hot. So there's no way to influence the variable temperature circuit. So what we introduce is something called reset strategy, which essentially says, okay, I want the space to be 21 degrees. Therefore, for every degree over 21 I am in the space, I want you to drop 5, 6, 7 degrees off the variable temperature set point. So you're kind of using the space to reduce your requirement. Why is that important? Well, look, let's be honest, it's less demand on the boiler. Therefore, can you start to reduce your VT set point? Going back to what I was saying before, if you're reducing your VT set point because there's a lack of demand, and you're maintaining your fresh air or your supply air from your main ventilation, then you can start to reduce your boiler set point, therefore reducing your gas. So now we get a little bit into the alarm management and alarm monitoring. So all the plant run hours are to be logged. For this site, we're gonna monitor and log all plant run hours. So we're gonna everything that we run, the boilers, the chiller, the fan coil units, the AHU. We're gonna monitor the amount of hours that they run, and we're gonna monitor on a week by week, week by month, and a month by year basis. And then we're gonna create an alarm if the change happens more than 5% from its last version. Because what clearly something's happened, something has happened, and that means that the hours are running longer. Now it could be a real scenario, it could be a frost condition which has generated that. We want to be able to notify people of that. As I just said, optimization is only as good as the last time the energy was optimized. So using energy alerts is crucial to focus on drift. If AHU cooling and heating valves are open together or within 15 minutes of each other, the BMS shall raise an alarm. Why? Well, usually, more than 15 minutes would indicate a fault and a poor use of demand. Even when you think about things like dehumidification, anything over 15 minutes is probably not. It's probably more at play there than a controlling element alone. Huge one. Monitoring the hand status on panel switches as a digital input within the BMS. More importantly, creating a cost per wasted energy alert. So what do I mean by that? Well, look, we're monitoring the HVAC equipment now. So we know if things, because we're monitoring the run hours and we're monitoring the hand status and we're monitoring the energy, we know exactly when something's being put in hand and more importantly, how long it's been in hand, therefore infer how much energy that's wasted by putting it in hand. It's crucial. I think sometimes even when people get notified that something's in hand, they don't really make the link of why that's important. Putting some real tangible value and costs against that is really important for the mindset. Without being disparaging here, untrained engineers, that's the first thing that tends to happen if you've got no knowledge of why the BMS system is holding a specific item of plant off. There's normally a good reason why that's the case. So therefore, the default action is to go and switch it into hand, and then we're human beings, right? So we forget, things just happen, and then days become weeks become months, and all of a sudden you've got crazy high bills and left unwarranted is not great. So again, monitoring the hand status is really good thing that we'll employ. A big one. So we'll all be familiar with the hot and cold calls, and there's a big load of research about where this comes from, and in reality, there's a link to what's called the thermal conductivity zone, which is a layer of your skin, which gives that feels like temperature, and it's a combination of humidity, temperature, and velocity or wind speed. So dependent upon how you deal with the different levels of that can really affect what that means as a feels like temperature. So oftentimes you could feel actually a lot colder than what it is. Why is it important? Well, drafts rather, the biggest cause of cold complaints, and the biggest factor is usually the velocity. So a lot of speed blown from a grill or a duct. So reducing the speed in cooling mode in the winter. So just let me say that again. Reducing the speed. So when a fan coil unit is in a cooling demand in the winter months, reducing that speed on the fan is key to reduce complaints, but also reducing energy because you're running the fans at lower speed. Not in heating mode, obviously, because that doesn't have the same effect. It's running the fans in high speed in cooling mode in the winter has more of an effect, especially with the combinations of humidity levels. Okay, so results. So we've we've gone through a whole host of energy conservation measures. We've put a new BMS system in. We have put in a new lighting system. We've removed and replaced the old motors with new VSDs. We put wireless sensors in and wireless relays that have now controlled the gas units a lot better. So we've provided a load of efficiency measures that the client is, really pleased with. So what do the results look like? Well, we come across the costs. So we equated all 4 of our initiatives together, and we got a total cost, delivered for £148,000. So what savings did they deliver? Well, electricity actually saved 17% on a year-by-year basis. So I saved 25.5, £100. And on the gas, way out on the gas, we saved 40%. By the time we took control of the boilers properly and we took control of the gas units, we saw a massive saving. So in total, we're saving £49,500 per annum across gas and electricity as a blended cost. So you think about that as a capital investment. You outlay 148k at the start of the project. In year 1, we take 49 or nearly 50k off that. In year 2, we take another 50k off that. By year 3, we actually start showing a positive gain. By year 4, quids in, and by year 5, everyone's sitting quite happy with the initiatives, but that can quickly dwindle if left unabated. As I said before, optimization is only as good as the last time the site was optimized. And so we have to provide continuous monitoring. We have to always be on top, using the things what we've just discussed and employed, which is round-the-clock monitoring, alerts to key individuals. So what are the benefits to that? What are the benefits to round-the-clock monitoring? So profile alerts provide real-time alarms where problems may arise. Traditional BMS systems, they alert to faults and conditions, but actually, it's the BMS system is so much more than just a piece of kit. It can and has the ability to do a whole lot more, and specifically no more so than when we talk about energy, and using it in a way to really start guiding how we monitor the day-to-day activities. Obviously, it reduces unwarranted inefficiencies. We can track energy conservation measures in real time through the same platform. So, if we decide later down the line we want to go and put a CHP in as an example because we want to reduce the base load further, and we want to maybe remove some of the boilers, then that's a really good way in which we can use that same data to track that energy conservation measure and see what that's done. We can improve employee energy awareness, so using that same front end dashboard to display on things like monitors in the foyer and things like that, because it's IP based, remember. And we can target sections of the business with targeted efficiency goals that can be tracked, again using the same platform. What considerations though do we need to make so far? So we've done a lot of stuff, right? We've made a lot of savings, and that's great, but actually if we take a step back, we need to employ soft landing solution to fully appreciate the full scale of the complexity. I'm going to go into what soft landings are in a second in more detail, but you think about it. A client will go to a consultant will, with a problem, the consultant will take that information from the client and then create a specification that will go out to many different people, and what originally started as a quite good idea, by the time it's delivered, often changes. And there's been lots of research and studies that show the disconnect between the point at which you deliver a project to the point of handover, and then the delivered results don't ever quite seem to be, what we first intended, or not we, but collectively as a sector. We need to consider employing perhaps a specialist to assist in an elevated handover process, and that's not just a handover. Actually, this is right throughout the whole coordination of the project. We need to be able to provide remote support or even specialized recipients who can receive the alert. So maybe the clients doesn't want the own staff or energy manager to deal with that, but actually wants that to go somewhere else. So that needs to be factored in. And employ regular BMS aftercare. That also includes the energy management. So not just doing your traditional point-to-point checks and, raising actuators and whatnot, but actually looking at energy, looking at ways in which the energy can drift and how we can be on top of that. So, as I say, we've just talked a little bit about soft landings, but it's really about risks. So the identification actually of risks, it requires a cultural change with how projects are delivered, and it's got to be collaborative. That is what soft landings are. It's got to get not just your consultants and your MEPs and your controls guys integrated, but actually the client at an earlier stage, so that they can see and collaborate together on how we deliver a project up until handover, because that's really the only way the adoption of complexities of systems are going to, come to fruition once the handover has came about. So this is a 5-stage plan that I believe BISRIA put together, which is actually quite cool, and I like the concept. So stage 1, inception and briefing. So this is a soft landing stage, 5 stage. So designers, constructors, and end users spend the time with the client to fully understand the needs, design objectives, and roles and responsibilities. So again, keeping the client at the heart of that. Stage 2, design, development, and construction. So the teams review the insights from other projects and engage in reality checking. So sense checking each stage of the build is really key. Stage 3, pre-handover. So the teams prepare buildings for handovers. That's the full teams, the MEPs, the controls, the specialists, the ICT infrastructure guys, the consultants even. So the teams prepare buildings for handover and ensure FM understands the systems. That's a big part of it, making sure there's that kind of soft landing piece. And that for me speaks to the heart of what a soft landing is. It's that aftercare and going into full operation. So then the initial aftercare phase, so the team has to deal with the emerging problems for 6 to 8 months. So again, collectively, no one burying their head, making sure that once the site's been handed over, we have a duty of care. We all have a duty of care when it comes to energy. We all see what's happening around us, so we have to. It's easy to just put your head down and move on to the next one, but actually, using your relationships, using them bonds to really create more of a partnership with clients actually than what a kind of move on to the next step would be. And then stage 5, apologies, an extension of aftercare. So operational performance is optimized through energy monitoring. I mean, that's exactly what we've spoke about all the way through this presentation. So, inspections, fine tuning, making sure loops are optimized, making sure everything that we've just spoke about is being championed. I think it's really, really key, guys, and really important. And I think that kind of gets me to the end of the presentation. I am a little concerned. I apologize. I tried to get that done in 45 minutes. It looks like it's about 50 odd. I don't know if anyone has any questions. Really appreciate your listening. I hope you, if anything, got some sort of appraisal from this, some sort of level of information or something that may help you in the future. Julian, is it worth handing over to yourself just as a closeout, and then maybe seeing if anyone has any questions?
There are a couple of questions. I can start reading them off, and then if you want to address them. Yeah. I'm conscious of time, so maybe at some point we'll just call it a day. But I'll start off with Gareth Tinsley, who asks, would shutting off heating pumps negatively affect water quality?
You're not talking about having these heating pumps off for long periods of time. It's based on demand, isn't it? So you have to consider, and you would also have to employ routines to circulate the pumps, whether it was just circulating the pumps once a night for 5 or 10 minutes. You would employ some sort of a strategy that would mitigate any kind of issues with that. But it's a really good question.
As a follow-up, he actually says, using free cooling in the winter would require the AHU to be sized for cooling application and not just fresh air, increasing size and capital costs.
Well, in reality, if you think about it, your AHU you are providing fresh air from the outside. You have a level of fresh air that you have to upkeep. Things like, as an example, you may be trying to introduce really cold air, so you have to make sure it's heated up to its minimum level, which is maybe somewhere between 8 and 12 degrees. But actually, I don't see an issue from free cooling. I get the point. You're right. Is in that it has to be, the ventilation system in itself has to be adequately sized in order to equate the amount of free coolant to facilitate the occupancy. But even in that scenario, what you're trying to do here is you're never gonna provide the full suite of everything, but actually reducing the amount of energy used. So if you have to have some level of free cooling with a small amount of mechanical cooling, it's better than just running your chillers irrespective of the conditions. So we have to be always thinking of how energy efficiency has to be the front runner before mechanical cooling. But again, it's a good point and well made.
Next, we have Richard Hilliard. He says, soft landings is more than handover and aftercare. Yes, this is a big component, but soft landing success criteria need to be adopted in inception and followed through with design and construction prior to handover and aftercare.
I think he probably said that before he saw the last slide.
Fair enough. A question that's just come in from Les Ingram. What's your view of seasonal commissioning? Does this provide a further worthwhile cost benefit for more normal handover protocol?
I do. I definitely think that's a really good point. It's making sure that your plant is fit for weather for any weather conditions, and this is where, for example, things like forecasting reviews really come in handy. So you can automate your software to deal with the changes in weather and how that influences the building. So definitely is the case. I was actually talking yesterday, literally, with one of my colleagues, Adrian, about that very topic. It's definitely a good consideration to have for sure.
Okay, fab. I think that actually comes to the end of all the questions. So unless anything comes in the next few seconds, I guess we'll call it a day.
Okay.
Yeah. All right then.
Fantastic.
Okay, well, thanks
you actually
everyone.
Finished on time, which is good.
Yeah, no, it's good for everyone, I think. It's nice. But yeah, thanks for coming to this Home Counties Northeast event. We will do the usual follow-up, so we can send certificates of attendance, and once it's all ready, we'll send over the video for the second session along with the first session as well. So that's all there is left for me to say, really. I mean, is there anything you'd like to close out with, Andrew?
No, just this as I say, this is the second edition. The plan is to keep on picking up key topics, not always trying to educate, but sometimes even trying to pose poignant questions where it's open for debate. I love the idea about challenging anything, because no single person is right, but you have to always have a mindset of trying to challenge the status quo for obvious reasons. So for me, we're going to continue with these kind of series, and the first one was CPD certified, which is fantastic actually. So at some point we'll be trying to get around and educate a little bit further, and yeah, there'll be more to come. So thank you very much for being online and watching through.
Fantastic. Cheers, Andrew. Cheers, everyone.
Cheers, Julian. Thank you, guys.
Cheers. Bye-bye.
Cheers, Andrew.